Welcome to Chapter 1, an introduction to physical chemistry. We will explore the fundamental physical principles governing chemical systems. The aims of this video are to explain the physical principles governing chemical systems and describe the 4 areas of physical chemistry. This video will cover an introduction to physical chemistry, thermodynamics, its systems, equilibrium, properties, temperature, pressure, and ideal and real gases. Physical chemistry studies the quantitative aspects of chemical phenomena. It's divided into thermodynamics, quantum chemistry, statistical mechanics, and kinetics. Thermodynamics is the science of energy and its transformations, involving heat and work. A thermodynamic boundary is the separation between a system and its surroundings. Boundaries can be rigid or non-rigid, permeable or impermeable, and adiabatic or non-adiabatic. A thermodynamic system is the chosen region or matter for study. The surroundings are outside the system, and the boundary separates the two. Thermodynamic systems are classified into open and closed systems. Open systems allow both mass and energy flow across boundaries. Closed systems allow only energy transfer, not mass. Isolated systems have no interaction with the surroundings. Neither matter nor energy is transferred between the system and its surroundings. Thermodynamic equilibrium is defined by no changes in macroscopic properties over time. The types of equilibrium include thermal, mechanical, phase, and chemical or material equilibrium. Thermal equilibrium exists when two systems, or a system and its surroundings, have no net heat exchange. Mechanical equilibrium relates to pressure. It is reached when there is no change in pressure over time, meaning the net force on the object is zero. Phase equilibrium occurs when the mass of each phase in a multi-phase system reaches a constant equilibrium level. Chemical equilibrium means the chemical composition of the system does not change with time, indicating no net chemical reactions are occurring. Thermodynamic properties are either extensive or intensive. Extensive variables, like total volume and mass, depend on the system's size. Intensive variables, such as pressure and temperature, are independent of the system's mass. The zeroth law of thermodynamics is related to temperature and states that if two systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. The temperature scale is defined by the ice point at 0 degrees Celsius and the steam point at 100 degrees Celsius, both at 1 atmosphere of pressure. We use the Celsius and Fahrenheit scales. Temperature conversion units include the following formulas. $text TR equals 1.8 text TK. Dollar and $text degree text F equals frac 95. Text degree text C plus $32. Pressure is defined as force per unit area. Units of pressure include $1 text kPa equals 10 to the power of 3 text N per meter squared dollar, and $1 text MPa equals 10 to the power of 6 text N per meter caret $2, which equals $10 cubed text kPa dollar. Ideal gases, or perfect gases, are characterized by the relationship $text PM equals ρ text RT dollar. Gases behave ideally at low pressure and high temperature, where their density decreases. The gas constant, R, has various values depending on the units used. Boyle's law states that at constant temperature, the pressure of a fixed amount of gas is inversely proportional to its volume. Charles' law has 2 parts. First, the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. Second, the pressure of a fixed amount of gas at constant volume is proportional to the absolute temperature. Avogadro's principle states that the volume of any gas is directly proportional to the number of particles at constant temperature and pressure. For ideal gas mixtures, Dalton's law states that the total pressure is the sum of the partial pressures of the individual gases. $text P equals text PA plus text PB plus $. Real gases deviate from the ideal gas law, especially at high pressure and low temperature. Deviations are measured using the compressibility factor, virial equations, and the van der Waals equation. The compressibility factor, Z, measures deviation from ideal behavior. It is defined as $text Z equals frac text PV text RT dollar, where V is the molar volume. For an ideal gas, Z equals 1. At intermediate pressures, Z is less than 1, favoring compression due to attractive forces. At high pressures, Z is greater than 1, favoring expansion due to repulsive forces. In conclusion, physical chemistry is the quantitative study of chemical phenomena. We've covered thermodynamic systems, equilibrium, properties, the Zeeroth law, and the differences between ideal and real gases.